Good morning, everyone. My name is Seung-woo Jo from KQC. Let me start by thanking all of you for attending our event today. Before we get started, let me outline today's event. This seminar consists of two parts. The first half is about exploring a quantum ecosystem, and the second half is on K-Quantum today. Most morning sessions are pre-recorded, but the afternoon sessions are mostly live. Each session will take about 20 minutes. Please note that there is no Q&A after each talk, considering tight schedules and fairness. If you have any questions about the presentation, please leave your comment and questions with your email address in the chatting window. We will reply after the event. Now, we are going to begin IBM Quantum KQC Hub Busan Open House. Let's start with a welcoming speech from Mr. Ji-Yoon Kwon, Chairman of KQC.
반갑습니다. 오늘 저희 KQC 허브의 오픈하우스 컨퍼런스 행사에 참여해 주신 많은 분들께 진심으로 감사드리고 현재 실시간 온라인으로 참석해 주신 여러분들께도 진심으로 감사드리고 환영의 말씀을 드리겠습니다. 저희 KQC는 지난 7월 1일부터 IBM 퀀텀 허브의 운영 파트너로서 상용화 연구를 시작하였습니다. 저희 KQC 허브는 현재 세계 25개국의 IBM 퀀텀 허브 중에 상용화 연구를 시작하는 유일한 허브라고 말씀드릴 수 있습니다. 저희는 지금 금융과 화학, 바이오, 제약 분야에서 활발하게 연구를 진행 중에 있고 지금까지 약 36억 건이 넘는 연산을 수행하면서 여러 가지 퀀텀을 활용한 그런 상용화 연구를 시작하고 있습니다. 최근 양자 컴퓨터 기술이 매우 빠르게 발전하면서 소위 양자 우위 시대가 이제 곧 시작되는 시점에 이르렀습니다. 이러한 시기에 양자 컴퓨팅 기술은 학교와 연구소에서 나와서 실제 현실 속에서 활용할 수 있는 그리고 또 여러 문제를 해결할 수 있는 그러한 상용화 연구가 매우 중요한 시점이라고 생각됩니다. 오늘 KQC 허브의 오픈하우스 컨퍼런스는 이런 시대적인 변화에 맞춰 산업 현장에서 양자 컴퓨터를 활용할 수 있는 여러 가지 주제를 중심으로 컨퍼런스를 구성하였습니다. 양자 컴퓨터 개발의 세계적인 선도 기업인 IBM의 제이간바타 부사장님하고 아파르나 파르카르 부사장님이 오늘 주제 발표를 하실 거고요. 또 저희 KQC의 기술 자문을 맡고 계신 연세대학의 이학비 교수님과 박경덕 교수님 또 흥미로운 발표도 있으실 겁니다. 그리고 특별히 국내 단백질 구조 분석과 신약 개발의 선두 기업인 바오밥 AI 바이오에서 또 신약에 관련된 여러 가지 발표를 하실 겁니다. 또 해외 기업들도 참여해서 흥미로운 주제 발표를 예정하고 있습니다. 모쪼록 오늘 KQC 허브의 오픈하우스 컨퍼런스 행사가 양자 컴퓨팅의 관심과 이해도를 높이고 산업 활용을 위한 국내 상용화 연구에 의미 있는 시작점이 될 수 있기를 기대하면서 여러분들께 감사의 말씀을 드리겠습니다. 감사합니다.
Thank you, Mr. Kwon, for the warm welcoming message. Next, we will have Ms. Aparna Prabhakar, who is the IBM Vice President of IBM Quantum Partners and Alliances. As an expert at building a quantum ecosystem, she will share her experience from other clients and countries under the title, Growing a Successful Quantum Ecosystem. Let's dive into her talk.
Hello everyone, I'm Aparna Prabhakar, Vice President at IBM Quantum. In this role, I'm responsible for development, growth, and delivery of quantum ecosystem at IBM. I'm very excited to be here talking to you about what we are doing at IBM with KQC. To begin with, let me tell you a little bit about our journey. In May 2016, IBM Quantum put the first quantum computer on cloud, and it is my true belief that that actually accelerated the rate of adoption of quantum computing as a technology. The numbers really speak for themselves. Today, we have a fleet of over 20 systems which are available to our partners to use. We have over 410,000 users 210 members in our quantum network who are doing 3.5 billion executions per day. From day one, it has been about one thing for us: adoption, adoption, adoption. And it is clearly evident in this exponential growth you see. In May 2022, we had 1.6 trillion lifetime executions on actual IBM quantum systems. Think about that, 1.6 trillion executions. We have come a long way since we put that first quantum computer on the cloud. And this is in part possible due to 210 plus members we have in our ecosystem. Out of the 1,800 papers which have been written on research being done on IBM quantum systems, 850 of them are by our partners. And these partners come in various shapes and sizes. They are hubs like Korea Quantum Computing. They are Fortune 500 companies. They are universities. They are research institutes. They are startups, and they are GSIs. But the one common goal of the entire IBM quantum network is developing the first commercial applications of quantum computing. IBM is partnering and engaging with industry experts to look at problems that are classically hard to solve and investigating whether the quantum computing could provide an advantage. We at IBM are in the business of building capabilities and providing tools to advance quantum technology. This is evident in many application areas that our partners are working with us. Here's a subset of the industry partners. Now, we won't have time to go through everything, but let me take as an example Woodside, an oil and gas company in Australia and one of our active partners. They recently published how to use quantum machine learning for a large set of data more efficiently by estimating kernels on smaller data samples. As we've been working with the members of IBM Quantum Network through years, we have realized the importance of training the future generation of quantum natives. By making a software development kit called Qiskit open source, we have driven open education and helped people to quickly familiarize themselves with quantum programming. And we've developed an active community where questions are asked, answers, and leading to further collaboration on a daily basis through social media channels. And of course, we are investing in the future by partnering with universities to help develop quantum courses and curriculum and offer internship opportunities to their students. Now let's get specific about Korea. Here in Korea, we've partnered with local institutes to organize and run quantum programming hackathons over past 2 years so that the Korean students can learn how to program quantum computers as well as learn quantum electrodynamics and superconducting qubit chip design. We have run 2 Qiskit Hackathon Korea events in February 2021 and 2022, each with over 200 participants from all over Korea. We've also supported hackathons hosted by SKKU Quantum Center for Korea Quantum Week at end of June 2021 and 2022, where students wrote Qiskit code to run on both IBM Quantum and IonQ systems to foster an open ecosystem. Through this effort, we are starting to see a growing number of Qiskit advocates and certified quantum developer. This certification identifies individuals with knowledge and proficiency in quantum programming using Qiskit. Our goal is to see over 1,000 certified quantum developers in Korea within the next few years. We want to develop the future of the quantum workforce here at Korea. We've also been working with our Qiskit community members to translate our open source educational material into multiple languages to grow quantum workforce across the globe. Today, Our documentation and tutorials are available in 9 languages, including Korean. Also, there is a great Qiskit Developer Certification preparatory course which is being created by one of our quantum interns at IBM, where people can not only get started on quantum computing, but also go through this course to become a certified quantum developer. These are all essential to our mission, which is to bring useful quantum computing to the world. We are connecting the best in hardware and the most advanced software advances to bring quantum computing to the users. And this is where KQC comes in uniquely. They are joining us in our mission to make quantum computing critical and useful to the world. They're bringing together research, education, and workforce development capabilities to the local industries and startups, which are essential to seed quantum computing in Korea. Thank you, and enjoy the rest of the open house.
I appreciate Ms. Prabhakar for her insight and advice. Now we have Dr. Hakbel Lee here. He is a professor from the Department of Applied Statistics at Yonsei University. Professor Lee has been offering lectures and intriguing students' interest in quantum computing since 2020. Today, he will give a talk titled Human Resources Required for a Quantum Ecosystem. Please welcome Professor Lee.
Good morning and good evening and good afternoon worldwide audience. My name is Hakbel Lee. I'd like to thank you for inviting me and congratulations for launching first quantum startup in Korea, Korea Quantum Company. Okay, I'll start. Okay, as you know, as a game changer, quantum technology is emerged. We are confronting the quantum revolution every week. Even some every day, we see some exciting news about quantum technology in the media. Nowadays, USA and several other countries have initiated quantum programs to develop this emerging market. However, quantum technology requires highly trained and skilled workforce. So how and what we, especially Korean, have to do when the times comes. So quantum technology system has an actual clear gap between research and industry. In other words, between academia and business. In practice, most students think, including me, think quantum physics and mathematics are so difficult. Most people perceive that only nerds can work with physics and mathematics. But fortunately, Richard Feynman said, nobody really understands quantum mechanics. So these words gave me encouragement. Nonetheless, we have to build the quantum ecosystem based on education, training, especially by university. As you can see, the fee 2021, as of 2021, there is a quantum effort worldwide. There is an investment dollars according to each countries. So there is one study, 2020, Fox et al., preparing for the quantum revolution. What is the role of higher education? In order to accelerate this quantum commercialization, the workforce must be equipped with necessary skills. Higher education has to optimize the important role for the training and hiring challenges that quantum industry is facing. Some types of companies in the quantum industry. First, quantum sensors, quantum network and communications, quantum computing hardwares, quantum algorithms and applications, and facilitating technologies, what the skills valued by employees. The company prefers the skills. I think there are two types of skills, as you can see in the screen. Shared skills across the quantum industry, and second one is variation skills required by the quantum industry. So how have existing employees gained the required skills? Training education programs would be helpful to teach the required skills and knowledge. Higher education role in preparing students for quantum career has been dominated by physics department. This is because it has mainly been in physics departments that proof of principle experiments have been carried out demonstrating quantum technology. The quantum industry is mainly interesting in solving real-world problems. Companies and industries does not want theory. They want to solve real problems. So physics education dominates the curriculum vitae for the quantum industry is slowly evolving as the technology mature into products that can be manufactured and sold. Company wants to apply quantum computation technologies to solve a real-world problem, or at least to demonstrate that it's possible to solve it. The goal is to achieve the solution faster than classical computer. This is why we have to adopt and apply quantum computing. They may also be involved with the development of new algorithms to learn on quantum computers. These are current the end users of quantum computing hardwares. I'm interested in quantum algorithms and its application. I think Korea Quantum Computing Corporation is interested also in quantum application field. So my classes related to quantum computing. First one, last fourth semester, I opened big data and quantum computing for graduate level, focused on quantum informations using Qiskit, quantum machine learning, and etc. Last semester, spring semester of this year, for undergraduate level, I opened the class, name is Qiskit for Data Science. This lecture includes understanding Qiskit and application algorithm using Qiskit, blah, 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 blah. Now, this semester, my class is a quantum finance computing. This is dealing with quantum value at risk, quantum bar, and quantum option pricing, and quantum optimization things. I'm my class students is trying to write some papers related to quantum finance computing. I plan the next year, next semester, next fall semester, spring 2023. I have a schedule for a new class, quantum computing for bioinformatics. This is why I'm standing now, because quantum computing, KQC is interesting in my classes. I'd like to expect the roles of Korea quantum computing, the two things. First, please be the global leading company as the first quantum startup in Korea. And second one is, please construct the a Korean model of the quantum ecosystem together with academia and industry. Time is so fast. Thank you.
Thank you, Professor Lee, for your insightful speech. I believe that we have to bear in mind advices from both Ms. Prabhakar and Professor Lee to build the quantum ecosystem in Korea successfully as quickly as possible. Next, we will have a 3 presentations on real cases for ongoing research and businesses under the umbrella of global quantum ecosystem. As you know, IBM Quantum has done various research with many global companies. Today, let's take a look at one of them, which IBM collaborated with JP Morgan Chase, one of the top financial institutions in the world. This presentation will be delivered by Dr. Nicholas Lovers. He is Quantum Global System Integrator Lead at IBM Quantum. It is another prerequisite speech.
Hello, everyone, and welcome to this talk on quantum machine learning on the Boolean cube for QKC Open House, October 19th, October 20th, 2022. First, I'd like to start by saying that this is joint work with my collaborators, Rudy Raymond, Muyuan Lee, and Antonio Metacapo at IBM Quantum, Tokyo and New York, respectively, as well as with Dylan Herman and Marco Pistoia from JP Morgan Chase, Future Lab for Applied Research and Engineering. The archive preprint is 2204.05286, and you can find version 1 of this preprint in there, and in a very short amount of time, we'll upload version 2 as well. So I'd like to start by discussing the motivation of what it means to study categorical data. So categorical data, as we all know from either classical or quantum machine learning, plays a very important role in a variety of algorithms and applications. And what it means to be categorical, it means to take discrete values. So for example, if you have a feature such as colors, color can be red, green, yellow, whatever, or it can be buckets of groups of ages, age group 1 to 10, 11 to 20, 21 to 30, and so on. So you are either in one bucket or another, and that is the discretization and hence the category. As far as finance is concerned, there are very many applications in things like fraud detection. Is a certain transaction on a credit card fraud, yes or no? Is a certain financial transaction money laundering or no money laundering, and so on and so forth. It also has a huge impact on credit worthiness and credit scoring. So credit score is also a bucketing game in which debtors are categorized in different categories of credit worthiness, say AAAs, AAs, and BBBs, and so on and so forth. So also very important applications over there. So we are going to consider supervised learning versions of these problems. So this means that we can either do like a classification. Is it going to be on this side, or is it going to be on that other side? Or, which is not topic at all for today, a regression. That would be very fitting for continuous data, which is not at all the data that we'll be playing with today. We can map a single categorical variable to multiple binary variables by doing a binary expansion. So for example, 0 will get mapped to 0, 0, 0, 1 will get mapped to 0, 0, 1, and so on, for instance, if you do it up to 7. So that means that as long as you can expand a digit from base 10 to base 2, you'll always be able to find that map that takes you from categorical data to binary data. Moreover, supervised learning problems with the categorical variables do map to learning a function on the Boolean variables, or, which is the same thing, the Boolean cube. I'm going to tell you more about it in a second. What is this Boolean cube? So suppose you have only 2 binary variables, 0 and 1, which I'm going to denote by B1. B1 can take value 0 or 1. So you will be on a straight line. It's either 0 or 1. That's fine. What happens if you tensor this with itself, and you can actually now, instead of having 1, you have 2 variables, right? B1 and B2. In that case, you are spanning a bigger space, a space which is made of 4 vertices, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so that is the Boolean rectangle, if you will, or Boolean square, rather. And you can still embed another categorical variable in there and call it B3. And in that case, you can still represent it geometrically with a nice picture. It will be this Boolean cube, and you have all permutations of zeros and ones, all the way from 0, 0, 0 to 1, 1, 1, 1. You can play this game a little longer up until probably B4 is the limit. B4 would be a 4-dimensional cube, which is called a tesseract, and that cannot be visualized in a 2-dimensional setting. So what you do is you project with a shadow. And just because you cannot visualize it, that does not mean that you cannot do quantum machine learning, or classical machine learning for that matter, or any kind of mathematics on that. So B4 would again have, in a complicated geometric object, all of the vertices of the data going from 0, 0, 0 to 1, 1, 1, 1. Okay, and you can map from a Boolean structure to the reals. And you can call this map F, let's say, and F will take a value on this categorical, on these Boolean values, and map to a real, like let's say 0.1, minus a half, pi, square root of pi, anything that you want. So this is one of the functions that we'll be studying today. Machine learning problems involve categorical data are really prevalent across many domains. They almost don't need too much of a motivation, but let's discuss it anyway. The range of a categorical variable lies in a finite set, and thus each element can be mapped to multiple binary variables for each member of the set. Now, our goal is to perform supervised learning, and this amounts to converting or mapping the problem into learning the function, a function on the n-dimensional Boolean cube, as we were saying. And we're going to use this variational quantum machine learning. We're going to use 2 different techniques from VQLM to fit the function f so that it maps accurately from B4 to R. We show, these are the main results of the paper, we show that for any function on the Boolean cube, there will be, so it's an existence theorem if you want, there will be a variational quantum model with n qubits, which is based on a technique called phase embedding, such that the output of this model agrees with the target function for all of its inputs. So that is kind of very nice, because it wouldn't be helpful if it doesn't agree with all the inputs, but it has to do this task in a certain sense, in a certain quantifiable sense, better than the classical algorithm. And this is something that we are going to get into very soon. Then we'll switch gears and take a different technique, which is called quantum random access codes, QRACs for short. And we will also demonstrate that for any function of degree D, if this degree D, if you take the number of, if you take n and you divide it by 3 and you take the floor of this, in case n is not divisible by 3 on the Boolean cube, then there will also exist a an ensemble on the variation of linear quantum models with n divided by 3 qubits based on this Q-rack. And the result is such that the output of the ensemble agrees again with the output of the target function for all of its inputs. So looking at this, you might want to say, oh, I want the Q-rack immediately because I'll have to use fewer qubits. Okay, there's some caveats to that. And we're going to test these two results for low degree functions. I think it was degree 4, 5, or 6. I will see very soon on the Boolean cube with IBM superconducting processors, quantum processors. So now that we've motivated these, I think we can advance to the mathematics. And we can say that the set of all functions on the Boolean cube forms a vector space of dimension 2 to the power of n. And in this, it's not any ordinary vector space. It's one embedded with an inner product, so Hilbert. And it's what you would think. You take a function f, embedded in a bra, take a function g, embedded in a ket, you close the bracket, and it's going to be the sum over f times g, and f applied on all the whole bit string, and g applied on the same bit string, and then you average by 2 to the power of n. Another concept that we're going to be needing very frequently is that of the Fourier transform of a Boolean function. So that will always be denoted with a hat. And in order to define it, I first need to introduce the character or Dirichlet character chi s of b. So it's defined as the product of -1 to the power of bi, where bi is in the string in the vector b, but the i's are chosen such that si is always equal to 1. So that will put a restriction on how many of these will be ones and zeros and so on. So the Fourier transform is, as you can see, it's an inner product of f and chi. So f acting on b, applied on b, and chi of s also applied on b. Now, a K-junta has a really interesting wording. It's a military term. Is a function on this Boolean cube whose output only depends on k of the input variables. So that means that the other n minus k variables will not have a say. So it's completely dominated or dictated by these k input variables. Okay, so now suppose that n in brackets, such as I'm writing in here, is the set of 1, 2, all the way up to n. And suppose that this set, j is a subset of this, and it contains k indices corresponding to the input variables that the junta depends on. The Fourier transform of a K-junta can only be non-zero on the elements from this set over here that I'm describing. So it's the set of all s's belonging in the Boolean cube, okay, such that for all I in this set n, that goes from 1 to all the way up to n, si equals 1 implies that I belongs in the set j. So that means that you can do better than get an upper bound. We'd actually get an exact result. So the cardinality of j will be the number of terms in the junta. So juntas are useful in learning theory for modeling learning tasks where the data can be explained only by a subset of the available features. So you can get rid of a lot of features that are not necessarily, or that are in fact not needed. So it helps a lot with data cleaning, data engineering, and so on and so forth. So scenarios typically occur when applying supervised learning to real-world data sets very frequently. Now, the Hamming weight is your distance from 0 to your letter in the alphabet, okay, like a typical, absolutely standard Hamming weight. And the degree of f is then defined as you make up a set, W of s, where W is the Hamming of s, such that for all s in the Boolean cube, the Fourier transform is not 0. Okay, so you make up that set and you take the maximum of that set, and that will be your degree. Okay, so now variational quantum machine learning, as the name implies, will have will also have a parameters that make up the gates in the circuit. Okay, so what this means is that you will have a state preparation first. Okay, x will be mapped to the amplitudes of your register, and you will undergo a unitary transformation that depends on gates. And these gates will be rotations typically, or control rotations, 1 or 2 qubit rotations. And what makes it parameterized is those angles. So perhaps maybe theta would make more sense to be written with an arrow on top to indicate that it's a set of angles. And then you make measurements, like some sort of tomography or some sort of selective measurement, and you're going to get your you're going to go back to classical, because this part here is quantum. The blue part will be classical readout. Okay, so you're going to have an output of a cost function f, and excuse me, the output of your function f, and you're going to compute its cost. Okay, so that will be the expectation of y minus the minus your function, and maybe it might be a moment. It might be the first moment, the second moment, so it might be a mean or a standard deviation or whatever, what have you. Okay, and you're going to make a choice. Are you happy with this or are you not? And if you are, then that's it, you're done. Otherwise, you're going to update these angles again, and you're going to go back to preparing the state, and you're going to run the whole variational quantum circuit again with the updated angles. And the process keeps repeating itself until you are satisfied with your cost function. Okay. Next, when applied to supervised learning, VQML consists of using these PQCs. You have as building blocks the embedding blocks and the trainable blocks, okay, which is where your angles are going to be. And your input data will be a set potentially from Rn, and it'll be stored on classical memory and can be embedded in a quantum state by utilizing a quantum embedding technique, such as the ones that you see, state preparation or amplitude preparation, and so on and so forth. The variational linear model is this function f. So depends on your angles, depends on x, and is defined as the trace of this operator h, which is an operator that belongs in the span of. So it's made of poly gates, right? Identity and poly gates. And what you do is you take these poly gates and you tensor them many times, m times, and the span of that is where your h operator will reside. Okay, and there's another w, which is your PQC, and another rho, which is defined as u acting on your zero registry, and then as a get, and then u dagger, so the Hermitian conjugate, acting on your zero registry, but as a bra. Okay, so you can make out these quantities, and you keep them in mind for the calculations that will follow shortly. Now, phase embedding that we are going to investigate was actually, we're not the first by any means. It was already considered by Maria Schultz for continuous valued inputs. So you might ask, you would think, well, if she's already done it for continuous, what is the point of doing it again for discrete values? Well, the thing is that they showed that if the phase embedding is repeated r times sequentially or in parallel, then the output of the variational model is expressible as the rth. Should not be a cubic here. The rth partial sum of a Fourier series, such as this one right here. And x is your n-dimensional input. So the trainable blocks and observable controls are these Fourier coefficients over here, the C omegas. If we assume the freedom to choose arbitrarily deep trainable blocks, which is, quite an assumption, and an arbitrary observable, then a model using this embedding can approximate any function on the circle, 0 to 2 pi with L2 norm, to arbitrary small error using sufficiently many repetitions R. Instead, what we do in this paper is we show that a variational linear quantum model using the phase embedding, which implies that R is equal 1, can express any function on the Boolean cube if an arbitrary observable can be used. So I don't have to repeat it that many times. It's okay to just do R equals 1 for us. So less expressive data, or data that has more restrictions, but fewer repetitions. And for her, perhaps better data, but more repetitions. Okay, so moving on, the linear quantum models. For the variational linear model, we already discussed, you have your trainable, you have your zero registers, and then trainable, and then W. And for the quantum kernel methods, what you're going to do is you're going to have a unitary transformation, and then it's permission conjugate unitary transformation. First, you're going to output the expected value, and you're going to compute the loss and update the parameters, just as we discussed. But with the quantum kernels, what you're going to do is output a probability distribution of observing all zeros. And the kernel method could be, for instance, a support vector machine, or a classification and regression, or something like that. The Boolean phase embedding is a variational linear quantum model. Okay, so what we're going to do is going to use 6, and we want to have a number that is divisible by 3, so that we can compare it later to QRAC. So what will be 6 qubits starting in the 0 position, then applying these X gates on them, and then a Hadamard. So that's my UB component. And this ansatz over here is, I believe it's called the universal ansatz without cyclicity. So producing a layer of rotations in Y, a layer of rotations in Z, and entangling qubits 2 at a time. But so by that I mean that qubit 1 gets entangled to 2, 2 to 3, 3 to 4, and so on and so forth. But when we get to 6, it does not recycle itself back to 1. Okay, that's kind of an important feature. And you can repeat this as many times as you want. Here we're going to do it 1, 2, 3, 4 times. Well, 3 times, 3.5 times if you want, and then measure. For every function on the Boolean cube, there exists a variational linear quantum model with a phase embedding that can learn it. That was the result. Okay, the QRAC is less expensive in terms of quantum resources. And as we said, if you take 6 and you divide it by 3, which is the feature of the paper, then that will make 2. Okay, so we don't need that very many qubits. Instead of 6, we're going to use 2. The UB portion is similar, because it'll be made of RY and RZ rotations, but there will be a much more complicated angle going in them. And this angle, of course, will depend on the binary strings. The W component will also be much shorter, made of RYs and RZs, and with entanglements in between them. Okay, the ensemble of the models will be such that you have this data labeled or unlabeled, and it'll go into different models, and then you make a prediction. Okay, so any function on an n-dimensional cube with degree less than or equal to n divided by 3 ceiling of that can be learned by an ensemble of QRAC embedding based variational linear quantum models on n divided by 3 qubits. For simplicity, let's assume that n is divisible by 3. And a k junta with k less than or equal to n divided by 3 certainly satisfies this condition. So the experiments on quantum hardware, sorry that this did not come out very clear. I think the degree here is going to be, so G3, A1, its coefficient, -1 to the power of B1, A2, and A3 also as coefficients of the -1s. When doing this with phase embedding on the Guadalupe machine, we were able, and on a simulator as well, we were able to get fantastic predictions. Okay, the targets match exactly what the simulation predicted and what the hardware predicted as well, or nearly, in order to account for noise. The QRAC embedding was surprisingly similar as well. Perhaps a little bit more precise even on certain Fourier coefficients, although this one was kind of, it was missed by both phase embedding and QRAC. Okay, the coefficients of A1 were 1/2, A2 was -1/10, and A3 was 1/4. You can change them and you'll get slightly different results. And we picked fractions that helped a little bit with the noise, I have to admit. Now, with a much more complicated 6-bit experiment, we're taking more complicated, more complex truth functions here, -1 to the power of B1 plus B4, B1 plus B5, B2 plus B4, and B2 plus B5. And For the most part, the results were very satisfactory. For the face embedding, there was just a little bit too much noise, so therefore we decided to go for simulator, and the simulator did agree very much with the targets. And the Fourier spectrum was also very satisfactory. The QRAC, because it uses fewer qubits and it's not as deep and so on and so forth, it lends itself very well for the hardware. And most of the results were surprisingly good, except perhaps for this outlier over here. Okay, so future directions for study are, study the ability of such models and generalize to unseen data. One thing that we didn't touch upon was the quantification of the required number of training samples needed to learn these functions. So something could be said about that. And benchmarking these models that use QRAC embedding. Identify cases where we can exploit the structure of the problem to design efficient algorithms. And the size of the circuits, just how shallow can they be, or how much do we have to go in terms of depth. Thank you so very much for your time. It's always a pleasure to present this work and future work at KQC. Please don't hesitate to contact me if you need to. You can reach out to me at nicolasrobles@ibm.com, and you can find out more about IBM Quantum at ibm.com/quantum. Thank you so much for your time.
Thank you, Dr. Roberts, for sharing his work in this session. Our next speaker is Dr. Tommaso Tumari, who is the CEO and co-founder of Entropical Labs. Entropical Labs, a member of IBM Quantum Network, is a Singapore-based quantum computing company, developing tools, algorithms, and software for quantum optimization. Dr. Tumari will give a presentation on the topic, Entropical Labs, the Quantum Software House. Let's listen to the speech.
Good morning. Good afternoon, everyone. My name is Tommaso. I am the CEO and co-founder of Entropical Labs. So it's great to be here. I would like to say my thank you to Kyun Kim and to all the folks at KQC at Korea Quantum Computing. It's great to join. Very happy to participate at this open house event. Today, I would love to introduce you to our work at Entropical Labs. We are a quantum computing software company based in Singapore, and our objective is to make quantum computers useful. So let's go into it. As I mentioned, I'm the CEO of the company, and prior to starting Entropica, I was working as a postdoc research fellow at SUTD here in Singapore and at the Center for Quantum Technologies. And even before that, I got a PhD in quantum information theory from Macquarie University. Actually, one of the reasons why I'm here today is because of something that IBM did. When IBM put the first quantum computer on the cloud in 2016, it was a big aha moment for me. It was the realization that the technology was becoming an industrially relevant technology. And especially at the time, it also offered me the opportunity to test a lot of the theoretical work I was involved with on a real quantum computer. And I spent quite some time discussing the potential and the opportunity in quantum computing together with Yuan, who today is our CTO and my co-founder. He was a PhD candidate at the Center for Quantum Technologies, and he shared a lot of the passion that I have and that I had at the time. And we were wondering, how can we use our unique set of skills to help accelerate the process of making quantum computers useful? And the answer for us was to quit our academic jobs and start Entropical Labs in early 2018. And since then, it has been quite an exciting journey already. We've been working with some of the best quantum hardware companies, including IBM. And in March 2020, we raised a seed round of 2.6 million Singapore dollars with some of the best investors in the region, including the Singapore government via SG Innovate. You can see that there's a lot of milestones here. I will get back to some of them as we proceed. But first of all, let me start by sharing with you some of our thinking. Why do we need companies like Anthropica? Well, we like to say because quantum computers are aliens. The reality is that it is incredibly hard to make them compute something at all. And it is even harder to make them compute something faster than classical computers. For classical computers, this is really not the case. Today, we have software interfaces, high-level languages. We have everything we need to communicate effectively with them. But with quantum computers, really is like trying to speak to an alien. The logic they follow is different, and the computational paradigm is very different from classical computing. So what role do we play as a company? What we do is building the software interfaces, which means the enabling layer to unlock the power of quantum computing. And our focus is on making quantum computers easy to use, accessible, and ultimately useful. This is what we do at Anthropica. Something very unique about our way of working is what we name the hardware-driven approach. It really means thinking about the quantum computing experience from the bottom up. It means starting with the devices, using the quantum computers as much as we can, understanding what are the unique features of the different platforms, and also understand what are the limitations of the platforms, so that we can use them in the most effective way. And from the very beginning, we've been collaborating with superconducting quantum computing companies like IBM and Rigetti, and we've also worked with trapped ion devices like IonQs, and also Honeywell's quantum computer. Now Honeywell, as you might know, has joined forces with Cambridge Quantum, and the new company is called Quantinuum. But especially when we extensively use their devices, they were still branded Honeywell, and this is why I'm using the logo for this presentation. We have tens of hours on these machines. In fact, we spend hundreds of hours running quantum computations, which is incredibly exciting having that opportunity. And it has made us very knowledgeable in terms of using the devices and also understanding what is going to be needed as we progress. And what is the aim of our work, right? In very practical terms. Well, for us, it's all about removing complexity. And as you can see here, there is a bit of a ladder happening. So up until last year, it was about removing the complexity of testing with quantum computers. But we are now past that phase. The phase that we are into right now is the experimentation phase. So we say removing the complexity of experimenting with quantum computers. And the next stage will be about removing the complexity of working with quantum computers and going all the way to generating value with quantum computers. This is how we think about our work, right? If you're a user of a quantum computer, we want to make it as simple as possible to use the device without having to worry about the complexity, for example, of the physics or the unique features of the modality that you might be using. Okay, that's nice to say, but how do we implement this vision in practice? I think the best way, as always, is to share experiences, is to tell a story, right? So we started in 2018, we were using a handful of qubits. And here you can see some code I had at the time. This code I've written is, I know it's not great, but I hope you can appreciate the effort at the very least. And if you can read the comment, I hope you can. What the comment on top says is that the tricky part now is to write down correctly the unitary of the computation. Why? Because at the time, this was on the Rigetti device, and it says nothing about the Rigetti interface specifically. This was the case for any other machine available at the time. We were still thinking in terms of single unitaries, initialize a register, perform Hadamard gates, perform rotations, and so forth. Well, the barrier with quantum computers was really thick then. How did we proceed from there? But before I move forward, I also want to emphasize that our focus at Anthropica is on optimization, specifically combinatorial optimization, and how we can use quantum computers to solve optimization problems. And the algorithm, or the family of algorithms that we have chosen as a main focus, is QOA, the quantum approximate optimization algorithm. Sure, most of the people who are listening to this talk are very familiar with it, but if you're not, It is a variational technique that you can run on today's quantum computers, which is great because it gives you a very valuable testing ground. And it can also be used to solve optimization problems. Okay, so let's go back to our journey, right? 2020, we're using more qubits. As you can see, we're taking a more algorithmic approach to, in this case, building QoE techniques. Here specifically, we are not using 12 qubits, but this was the average of the qubits that we used at the time. And you can see that we're already thinking about, returning QASM code and not having to code unitary by unitary. We got smarter here. Starts to look a bit more Pythonic, if you like. But also today, we can use up to 80 qubits. This is what we have access to. And we have open QoE. The barrier has been removed, and now we can talk to the alien. We can talk to the device. You will wonder, what is open QoE? It is a Python library for optimization with QoE and its variations on quantum computers and simulators. This is timely because the archive paper just came out a couple of days back. OpenQoE is available on GitHub, so I strongly encourage you to go and have a look at the reference, and you will find links to the documentation in the GitHub page. It's open source, so all of you can start using it and have fun with it. And it already integrates with IBM's, Rigetti's, and AWS brackets available gate-based devices. And we are now working on implementation with Microsoft Azure as well. So why do we need an SDK, which is OpenQoE, right? Why do we need a software development kit? Because ideally what you want to do is to create and run QoE workflows with 3 lines of code. And this is exactly what you can do with OpenQoE today. You define a problem, which is something you don't see in this slide. You initialize a model. You compile the problem instance onto the model, and then you optimize, and you are done. It's very powerful. It's a great way to quickly and seamlessly experiment with quantum computers on optimization today. And why did we build it? Well, because running variational algorithms for optimization problems, or more in general, requires a lot of effort. And now we're giving you some of the insights on the kind of effort that you need to really give to this kind of work. You need to set up optimizers to update the parameters. If the QPU connection breaks off over the network, this is a problem because you're going to lose all the data. You might have to rewrite the entire circuit if you want to run it on different hardware, and so forth. So the great thing about OpenQoE is that it solves all these problems for you. So you can actually spend your time focusing on the problem that you want to solve, on experimenting with quantum computers. You don't have to worry about all the subtleties that happen in the background. It goes back to our aim, right? We want to make it as easy as possible to experiment with quantum computers today. And here is a short example, just a snippet of code for you. If you want to solve a number partitioning, which is a very well-known optimization problem, where you have a list of numbers and you want to separate them or label them so that the sum of the numbers in the 2 partitions is either equal or as close to equal as possible. Well, all you need to do is to define your problem statement, then import a class, in this case, the predefined number partition class, write the QBO form of the problem, then create an object, a QoE object, compile, optimize, and get the results. It's incredibly quick to set up a problem and solve it using QoE with OpenQoE. There's more, of course. There's a bunch of useful utility functions. For example, if the problem is very small, you can brute force the solution and have a look at the ground state of the Hamiltonian, so you can compare the solution that you get with the theoretical solution. Of course, this can only be done on a small number of qubits, but it's a very useful tool if you want to start benchmarking whether things are working as they should. It's very easy to retrieve optimization data. And what OpenQoE gives you is a very extensive collection of information about the whole optimization routine that you have run. And you can also plot the optimization history, so you can actually see how the cost function has been evolving with the number of function evaluations. So the idea here is to give developers a tool that gives a more comprehensive experience when it comes to solving optimization problems using QoA on quantum computers and simulators. About that specifically, it's very easy to switch between different simulators. Here we are using the Qiskit QASM simulator in this example, but there are quite an extensive set of local simulators supported, including Vectorize, which is Anthropic's own simulator for QoA. It's a very fast one. But if you want to transition to a QPU, it's incredibly easy as well. You just need to take all the information about your account, and here we're using the IBM Q account as an example, and then continue as before. It's actually a really powerful way to work. And as you can see, you don't really need to change a code. You just need to change a line, and you're good to go. Our encouragement, of course, is go and try it yourself. So there's multiple example notebooks on the GitHub repo. You should go and try it out, leave comments, interact with us, really let us know what is missing, what you would like to see. We're here to help. We are here to nurture the community. And if you want to give us direct feedback, we actually have an OpenQA Discord already live. This is the link. I'm afraid since there's a presentation, you will have to copy paste it and join it. Otherwise, you can reach out to us and we'll be very happy to direct you to the Discord channel. Okay, I think I was a bit faster than the 20 minutes that were given to me. Hopefully you will be grateful for that. Again, thank you so much for the invitation. I hope I managed to give you a nice overview of the kind of work that we do at Anthropica. As I mentioned, we are based in Singapore. We're a team of 13. Our focus right now is on optimization and building software interfaces to make your work on quantum computers as useful as possible. Here you can see my contact, the company's contact, and if you want to get in touch and know more, all you have to do is to write us an email. Thank you so much and have a great day. Enjoy the event.
I really appreciate his excellent presentation. From the stories of JP Morgan and Anthropica Labs, I witnessed that many companies have already joined the quantum journey. I can feel that the quantum era is not far off. The last presentation in this session will be delivered by Dr. Blank, founding partners of Data Cybernetics. Data Cybernetics is a German company investing effort, brainpower to quantum algorithm design and implementation. Dr. Carsten Blank will give a presentation today. Scalable cloud access for quantum computing, a science to business perspective. Let's pay attention to his recording.
A warm welcome from Germany. My name is Carsten Blank and I am the Managing Director of Data Cybernetics. I am happy to have you here as my listeners today. May I take this opportunity and congratulate you on your way into the journey of quantum computing, a subject very dear to me. Today I want to talk about our company's projects in total, the product visions that we strive for, and all the technical solutions that we propose as the challenges of these go by. In particular, as the title suggests, I want to talk about our scalable cloud access to quantum computing. My interest in quantum computing is more than a mere fascination. Together with Professor Daniel Park from the Yonsei University in Seoul, we participate in research in an internationally recognized level. It is this combination that lets me speak as a person that looks on quantum computing from a science to business perspective. Thank you very much again. Let's start.
Let me first give an introduction to Data Cybernetics. We are a technological and scientific consultancy that helps businesses to tap into innovative solutions. Our emphasis on applied research and scientific programming supports our clients' claim to stay on top of technology. The strong focus on software and data engineering brings our technology visions to life. Our job is more than just innovation and consulting. We deliver 24/7 capable solutions. Our company was originally founded by Philipp Leser and myself in 2016. With our recent growth, we scaled up from a consultancy only to a technology startup in 2021. We are located near Munich, Germany, in the town of Landsberg. In order to learn more about the kind of projects we have done with clients, let me go through these on a high level. We have been working on optimal technical and commercial control of virtual power plants, demand forecasting in logistics, energy trading algorithms to benchmark the performance of an energy trading desk, energy consumption forecasting, time of usage optimization for smart charging, route planning in warehouse logistics, predicting delay of railway traffic, an interesting and ongoing project visible to all German railway customers. Associated to this project, we also have massively parallelized batch and stream applications, ancillary service market outlook predictions for offshore wind systems, and finally, software consulting for a quantum hardware scale-up. As you see, the list is long and showcases our expertise in a number of different areas. Since the beginning of this year, we have been granted government money to develop the software for a quantum computer. I will go into some more detail on this project, which is called RIMEX-1, funded by the Ministry of Education and Science. In its wake, two projects have been commenced as spin-off technologies, the Q-Alchemy product portfolio and the HTO API framework. Within these projects, first visible results, accessible for the public, shall come in existence in the next months. Let us describe them. Our own suite of quantum computing related services, which we call Q-Alchemy. This project has two initial products. A product that supports in converting your data into quantum data. This product has been the result of research with the University of Pernambuco in Brazil. Also, the optimization platform that solves QUBO problems with semi-automated decision-making on which of the solver, the Fujitsu or Gurobi, a mathematical QUBO problem is to be solved. A technology framework that we are developing for fast product development is the API framework HTO that enables us to scale quickly in an organized and extensible way. Its inherent AI capabilities will help us integrate machine-to-machine systems easier. The RIMEX-1 project constitutes a serious involvement with quantum computing. Based on ultra-cold atoms that can be treated as Rydberg atoms, the Rydberg blockade effect is used to solve certain mathematical optimization problems. The project envisions the construction of the lab equipment, the control hardware, and the software to control the system state. Also, connecting the state to the cloud and handling HPC requests is an important feature. This project constitutes one of the few big research projects that the government has accepted and is funding. Its main objective is to connect users to this cold atoms Rydberg quantum simulator. The algorithms to solve are unit disk maximum independent set problems using quantum annealing or the quantum approximate optimization algorithm. The users shall be mainly HPC clusters. Hence, one must handle thousands of nodes that each needs to solve a subproblem on a quantum computer. Generally, all problems shall be encoded in QUBOs, quadratic unconstrained binary optimization problems. Additionally, a benchmarking will be undertaken to show the current quality of service with respect to the current state of technology of optimization. Our mission in this context is to create the middleware, the software that connects the users to the hardware. In this respect, we are implementing access and job management, handle IT security, and settle the usages in a procurement step. On the other side, we will create the control and planning of laser pulses and readout, as well as monitoring and analytics. Our company is central in this project as it touches the most important parts. As we also have a strong commitment to science and research, We are looking forward to great collaborations and many deep tech learnings. Q-Alchemy now is our own commercial suite of quantum computing related products. We are aiming at providing a computational platform that will be able to solve computationally expensive calculations within an HPC-ready framework. We are implementing a spin-off system from RIMAX-1, one that will use the Gurobi and Fujitsu solver to handle optimization requests of Cubo-encoded mathematical optimization problems. But we are also edging into modeling of energy systems, their market outlook, and contracting modeling. Maybe we'll have the chance to handle certain chemistry-related problems also over the platform. One of the most exciting topics I personally find in quantum computing is the issue of compiling an algorithm to a quantum architecture. In this spirit, my collaborators from the University of Pernambuco and I have devised an algorithm, the so-called bounded approximation error algorithm, that supports to bring data into the quantum world. This is a computationally complex algorithm that profits from our platform. This service will go available within the next 3 months with all features necessary for a full digital product. Here we see the architecture of our computational platform. It handles computationally intensive tasks given from users on the left. These are either humans using website or programmatic access through SDKs. The API hands out resources and takes tasks or actions to modify resources. Events let the user keep track of long-running jobs. The cloud-based architecture handles all necessary details, like job management, identity and user management, monitoring, data storage, and of course any pre- and post-computations. In this image, we have put the optimizers on the right to show the target of the computational loads. The bounded approximation error algorithm, or BAA for short, has been broadly introduced 2 slides ago. Its goal is to create from data, we mean classical data, a quantum state, which has significantly fewer entangling operations for an adjustable error. This can improve the end-to-end performance of any algorithm greatly. An example can be seen in an image here, in which my collaborators and I compare the state-of-the-art method and its performance on real quantum devices, in this case the IBM Q, versus the BAA applied to the IBM Q. The results truly speak for themselves. The principal idea is shown on the right. Given data, a state vector, one finds a low entanglement substitute with optimal fidelity. Thus, from the partitioning of the quantum spin system, the proper circuits and pulses can be created. The Q-Alchemy is a full product, not a proof of concept. It involves user management, subscription and payments, tracking and auditing, full control over the computational loads and the graphical user interface, as well as SDKs for programmatic access. Furthermore, we have EU level of legal documents handling contracting details and general data protection regulations, or GDPR in short. Our API framework we have named HTO. This API framework is used on a microservice architecture with an AI-enabled dual human/machine-to-machine interface. This framework is our flagship technology with which we want to solve tomorrow's web-based challenges, namely natively adding machine-to-machine support as well as AI-driven decision-making. After all, this framework will support all our and our clients' digital product ambitions. Here we take a glance on the 4 pillars on which the goals of this API rest. The technologies that make up these frameworks are hypermedia, task-based API, event sourcing, and push notifications. These technologies thus enable organizationally scalable architecture, meaning that teams can be efficiently deployed, generic and extensible, auditable and explainable, AI-enabled, meaning that we have semi-autonomous decision-making integrated. Thus, we have a scalable human-to-machine and machine-to-machine interface. Now it is time to unveil the meaning of HTO. It is rather a technical term, Hypermedia Task Ontology. Well, now, next I want to talk about the business perspectives on quantum computing in Germany. As Germany has its unique strengths, I want to highlight a few of them that we have perceived so far. We base our assessments on what we hear from the news, from personal conversations, and from government activity. Certainly, known internationally is the German precision. Albeit, this seems to be a myth when taken as a whole. In certain areas, this seems to be exactly true. Looking into quantum tech, we see many hidden champions that are active on an international level, provided the finest and most precise instruments or technology. Therefore, Germany seems to be a good location to develop a strong quantum hardware industry from which the world will nurture. We found applications of quantum technologies not only in the computational realm, but also most remarkably in the quantum sensing community. Also renowned is the strong intellectual capabilities that exist at Germany research institutions on the fundamental physics level. Recently, the German government has invested a substantial amount of research and industry funding to bolster Germany's already impressive standing. As the development of quantum technologies are on their way, we want to look into the customer market of Germany, the end users. In many parts of the country, middle-sized companies make up for the industrial strength on which its society is proud of. These are usually family-owned and have about 400 to 1,500 employees. Even though many act on an international level, they are local in the structure, meaning they are interconnected socially in their specific area. Many of these companies are either indirect or direct line connected to the automotive industry. For most, their businesses are therefore facing high price pressures from their bigger customers. It is therefore the most important task for them to reduce their costs and risks. Prominently, we see an interest in more efficiency in their applied R&D efforts, as well as increasing the level of digitalization and automation. But also, operative risks are a factor, and being able to decrease these is of high value. What we often hear is that computational bottlenecks are of little concern. They are not the biggest pain point. The spearhead of research is also not attractive, as often the technology is not matured and therefore introduces more risks rather than reducing them. Now, how does the business structure look like in Germany? What structural situation do we find? And I want to again stress that this is only our experience, and it may, in the end, be a lot different for others. As a consultancy, we are interested in giving interested companies advice on where and how to start on their quantum journey. Here is what we learned. The industries that we talked to were very focused on the so-called gain for the buck project. This means that the core of German middle-sized companies will spend money if there is an immediate or short-term payback. Investments in long-term gains or even risky ones are reduced to an absolute minimum. As already mentioned, most middle-sized companies are held by families. These are concerned about their social impact and the financial security of their employees, as with their companies. This makes them attractive employers and well-perceived businesses, but makes them risk-averse. Germany has introduced a tax incentive for research and development projects. The tax deduction scheme has indeed attracted many applications, but their effect is yet to show. According to the new tax law, up to 15% of approved R&D activities can be repaid by the government if the research is done from external sources. In fact, it is even 25% of total expenses if these activities were done internally. Therefore, there is a strong incentive to spend more money on R&D, an effect that will support consultancies and providers of R&D services. Currently, we see less investment on quantum computing from a majority of businesses so far, taking the structural situation at hand, and these incentives also playing out still will take some time. So the question for us is, what needs to change to tap into the champions of the German industry? In fact, quantum computing must reduce risks or costs. Can that be done? As quantum computing is a new technology, it will increase risks rather than decrease it. So it must mature in order to gain confidence in its value. Also, if it was to be shown that quantum computing must be adopted early in order to achieve great cost savings or exceptional risk reduction, many companies would invest in it now. Interestingly, while surely present, a fear of missing out decision-making is avoided when making business decisions, such that they are more rational. To summarize, the technology must clearly demonstrate superior qualities or must mature. Taking all these considerations of the German end-user industry into account, what are our goals? As a company, we are looking for customers. We are offering expertise in the already mentioned technologies. These are our expertise in the HTO API framework, in particular the support of digitalization. We are looking for customers with an interest in technical innovation. And of course, we are experts in consulting and are looking for clients in particular in data science, quantum computing, software engineering, and energy markets. Within the quantum technology, our goals are to support the NISQ era with our data to quantum Q-alchemy product and expand on this idea, while also building a computational platform as the optimization solver product. The scaling of our team and the technology development has been achieved this year, while we expect to find new customers and markets next year. At the end of our short presentation, it is my pleasure to thank you for your valuable attention. Now, let me leave you with some words of Feynman himself. Nature isn't classical, and if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it is a wonderful problem, because it doesn't look so easy. I think we're all on the journey just to find out how wonderful that problem really is. And together it is much easier, so I stand with my motto, progress is a joint effort. I would really love to hear from Korean quantum computing, and I wish I would have been here today with you in Busan. Now, I would like to finally thank you for your attention and wish you a very pleasant day with many good and insightful discussions.
I appreciate Dr. Blank for his informative presentation. And this is the end of the first session. Now we are going to have a break time for about an hour. The second session will begin at 1 p.m., followed by a break. Thank you again for attending the first session. And we are looking forward to seeing you in the second session as well. Thank you. Good afternoon, everyone. Before we start, we should announce some challenges in schedule. SWM was supposed to give a talk this afternoon, but they can't make it due to their urgent circumstance. So we have 5 presentations. We apologize for the schedule change. Now let's move on to the afternoon session, where we talk about topics on K-quantum today. It is going to be a nice chance to catch up the current status of the quantum computing industry in Korea. The first presenter opening the afternoon session is Dr. Jay Gambata, who is an IBM Fellow and Vice President of IBM Quantum. He will give a talk about KQC and IBM Quantum. Let's listen to his message from Yorktown.
Hi, I'm Jay Gambetta. I'm an IBM Fellow and VP of IBM Quantum. In the past 5 years, quantum computing technology has rapidly advanced. IBM put the first fully programmable quantum computer on the cloud in 2016. Then we introduced the IBM Quantum System 1, the first fully integrated computing system in 2019. Today, we have a New York quantum computing data center with more than 20 quantum systems. We have more than 400,000 users around the world. They're using our quantum computing services to explore applications across industry, education, and research. You can see the rapid progress of quantum computing's capabilities by looking at our development roadmap. Last year, we released the 127-qubit Eagle processor. Users around the world are already using it for their research and industrial R&D. Our metrics are already showing off the adoption of our systems. So far, our users have written more than 1,800 research papers. This progress has been truly remarkable. The performance of our quantum computing systems, represented by scale, quality, and speed, is continuously improving. We plan on demonstrating the operation of our 433-qubit Osprey processor by the end of this year. And now, recent advances in error mitigation will let us better utilize today's quantum computing systems to bring quantum advantage closer. Recent algorithmic advances like circuit knitting allow us to integrate classical computing as part of the quantum computing workflow. This will let us leverage both classical computing and quantum computing to optimize the various types of problems users may need to solve. Circuit knitting will enable us to tackle large computational problems. That's the future of computing we envision. We have to integrate classical and quantum computing together to bring a full solution to our users. Through our partnership with KQC Hub, I'm very excited that we are bringing this most advanced quantum computing technology to the users in Korea. There are many industrial areas that quantum computing solutions could help. Quantum algorithms could improve search and optimization techniques, which is especially important in the fields of logistics and finance. Algorithms like amplitude estimation guarantee a quadratic improvement over worst-case runtime of classical algorithms. Another technique that might benefit logistics and finance industries is quantum machine learning, or QML. QML maps data into a higher dimensional computational space that only quantum computers can provide. This would allow us to compute in ways that are beyond the reach of classical computers. QML might be useful for efficient classifying data with complex features. For example, this could be useful for applications like fraud detection. Chemistry and material simulations are another area quantum computers are naturally suited for. Improving our simulation of nature can have a fundamental impact on manufacturing industries that deal with chemical properties of molecules or materials. This includes pharmaceutical industries or any other industry dealing with materials and design problems. In partnership with IBM, KQC will be your key industrial solution provider. KQC will provide quantum computing services to users and enable industries to adopt quantum computing as part of their workflow. Your work in quantum computing has a potential to create a quantum industry in Korea, and a quantum industry could revolutionize Korean businesses and make them even more competitive. Building a quantum industry will take work. It will require close collaboration amongst research institutions and industries where scientific breakthroughs can easily transform into industry solutions. I hope you all start your quantum journey today and will be happy to be part of it with you. I hope you will allow us to help you to realize your vision. And KQC will be there when you need quantum resources and solutions. Thank you for your time and enjoy your day.
I appreciate Dr. Gambata for his insightful address. Without any further ado, I would like to invite Research Director of KQC, Dr. Kyung Kim, as our next speaker. KQC was founded aiming for the commercialization of quantum computing and building a quantum ecosystem in Korea. Dr. Kim will share KQC's view of the quantum computing industry and KQC's role within the ecosystem. Please welcome Dr. Kim.
Hello everyone. Let me introduce myself. I'm Kyun Kim, a research director at KQC right now. And thanks for joining our open house seminar and listening carefully. In this session, we'll talk about what KQC sees in the future quantum world. And let me get started. Yeah, KQC. Actually, we have very amazingly intuitive company name, Korea Quantum Computing. Actually, we had a couple of company names in our mind, and we decided to go with the most intuitive one, because most people are unfamiliar with word quantum computing in Korea. Let me describe current understanding on the quantum computing in Korea. When we say quantum computing, some people remind of quantum hardware such as IBM 16Q, IonQ, or D-Wave. But still, many other imagine the Ant-Man, T-Net, and Doctor Strange, and Time Machine, something like that. There is a huge gap between a group of audiences depending on their knowledge level. This is what I felt so far after start joining, working on quantum computing industry right now. Sorry to say, but companies are reluctant to adopting quantum computing techniques to their business since they do not see short-term benefits from this new technology. This is the point where we are standing at in terms of quantum computing industry in Korea. But this is a totally different story for the other countries. This morning, Aparna delivered her talk about quantum ecosystem from the world. We also had take a look at a couple of examples from the outside this country. Not only from their talks, but also from a lot of market research, we realize that we are some steps behind those top-tier countries in quantum computing world. KQC thinks it's time to take an action to move forward. According to Quantum Insider, they have more than 600 quantum computing companies in their database as of 2022. The graph shows the number of quantum organizations by date they founded. From the graph, we can see that year 2013 is a big year for quantum software industry. There are more than 10 companies founded in that year. Between 2018 to 20, there are about 40 companies also founded. Many quantum software companies already had 3 to 5 years of experience, which is huge in such an incumbent industry like quantum computing. So if we divide quantum industries into subcategories, we can realize that quantum software industry is much bigger than expected, at least in my personal point of view. That's because, especially in Korea, media and government investment is more focused on hardware. We think this is harmful for the balanced growth in the quantum industry, and we, KQC, wants to point out quantum software industry needs to get more attention than now. The potential of quantum software becomes more clear when you see the following graph, which is presented by Boston Consulting Group. You see? Okay. According to this graph, we can see that the proportion of investment on the quantum software is increased dramatically within just 2 years. It means that people start believing commercial quantum hardware will be available soon. So once it's practically meaningful hardware is available, it's forecasted that quantum computing is the fastest growing sector, which will be 3 times bigger than others in 2030, according to Quantum Technology 2030 report. Actually, we are not sure about how accurate those numbers are, but we can find reports with similar opinions very easily. I think this is kind of main trend, I think. Let us take a look at the survey from Ernst & Young on quantum computing industry. About half of people were positive about the potential of quantum computing, about 48%. About around 70% of them will initiate quantum projects by setting organization within 1 or 2 years. And they expect financial services are the area where quantum computing can be applied very quickly, and health, life sciences will be affected the most after 2026. I also was very amazed that there are already more than 40 quantum solutions or frameworks of different level with different target customers. It's like the very beginning stage of AI industry, which was about 10 years ago. This is what I feel at this moment. Then let's take a look at how quantum computing industry looks like in Korea. We usually call quantum technology, not distinguishing software from hardware, including both. Government reported that there are around 500 researchers who is working on the quantum computing related topics in Korea. Most of them are hardware experts, I guess. So comparing 5,000 researchers in China or 3,000 researchers in US, the number 500 is far less than it should be. So government recently addressed this issue and announced investment strategy on quantum computing industry targeting year 2030. Sorry about that. Sorry for showing you the Korean, but what it actually says that they have a vision of moving from digital to quantum era, targeting top four in the world in terms of quantum technology. As a part of a strategy, they will train about 1,000 quantum experts by 2030. I think this is a very good start to build a human pipeline to create a sustainable quantum ecosystem, but it's not sufficient though. Experiencing AI revolution, what we have learned was that building a community or ecosystem is a key factor for success of quantum computing. KQC will play an important role in this quantum wave. Among many items listed on the poster, these 4 highlighted items are what KQC can contribute to. Especially for the quantum computing area, which is colored in orange, we will carry out research projects on the quantum algorithm in joint work with the KQC members. We can contribute to HR development part, or left lower corner, actually, yeah. This is about HR development, and we will contribute this HR development via running an education program of different levels. And the building cooperative system and develop practical use cases are KQS's core missions, so there's no doubt. Many other quantum computing software companies seem to end up with the same conclusion. KQC also thinks that education, research, and business are 3 pillars of quantum ecosystem. These 3 pillars are contribute to ecosystem in time order. Starting with education, we carry out a research project to find out the use cases that can be scaled up to help our own businesses. For this, at least the 3 parties should be involved for quantum ecosystem. They are university or research institute, and the government or public, or commercial companies or private. You can group quantum ecosystems into 2 categories. One is the university-led model and the government-led model. So quantum computing is so innovative technology that companies cannot easily dive into. In this case, universities or research facilities are those who can lead the industry. The figure here is Waterloo University's Quantum Valley, led by Transformative Quantum Technologies team, so-called TQT team. The TQT and their research connects with early adopters, industry, and other stakeholders to develop quantum technology toward applications that deliver social and economic benefits. As an example of public or government-led model, Quebec can be another good example. Quebec Quantique is a company name, is an organization that leads quantum computing industry to the city of Quebec. Their mission is to use quantum sciences and technologies as a lever for the economic and social development of Quebec. They try to ensure that quantum technologies are adopted by a majority of Quebec organizations by 2030, and it shows how local government can support and lead the quantum industry. The Paris Reason case is another example of a government-led model. Institute of Paris Reason, which is a historical institute, recently positions the organization as a leading scientific and technical support center for the development and evaluation of public policies in the capital region. Its investment is more sizable to bring quantum equipment at the center of its ecosystem, and this is where KQC agrees on. We also believe that physical quantum computing is necessary for quantum computing in the industry to grow. Data security is another critical reason why we have to bring quantum computer into our Korean territory. So as you may know, we have plans to purchase IBM Q System 2 with the 433 or 1121 qubits starting from next year. Next, let me go over KQC's main services. On the right-hand side, the access service forms the basis of our services. And for now, we provide quantum access through cloud service, but we will provide direct access to physical hardware in the future. Education will be provided both to our members and the general audiences from the quantum community upon request. We will collaborate on the research projects focusing on the real-world applications as well. All these efforts we are making now will contribute to our members' quantum readiness and the opportunity to enhance global competitiveness, with no doubt. Here is what KQC wants to build in the Busan metropolitan area, and KQC will play as a hub of K-quantum ecosystem by introducing IBM Quantum System 2 and the Quantum Data Center. We will closely working on the research projects with the ETRI, Electronics Telecommunications Research Institute, which is a government-sponsored research facility, and both of domestic and foreign universities. Of course, there will be huge supports from the IBM Quantum Research Network as well. Also, we will work with IBM Quantum and Busan to commercialize quantum computing technologies. While building infrastructures for the quantum ecosystem, we will keep outreach to potential KQC customers to enrich quantum ecosystem. A brief look at the KQC offering, and it includes 3 main services that KQC provides, and the letter broke anyway. So it's A, R, E, R, those are access and research and education. And then all those 3 services are break down into components, and they will be provided in different format and different cycles. We are not sure about what exactly our members can get out of our quantum ready plan, but we can set expected milestones as follows. We expect our members are equipped with the quantum minds and teams with the practically usable quantum strategy by the end of year 3. The total project period will vary depending on the situation and circumstances, of course. And we have to say, welcome to Baobab A Bio. Our first member, we welcome Baobab A Bio as of October 1st. We are so excited and anticipate work with them, and we also press release is now being prepared to announce the collaboration between the Baobab A Bio and KQC in the help of IBM Korea. So welcome. Yeah, here this is like our kind of plan. Let me share our future plan by each main service area. We start working on the contractor for IBM Q System 2, and hopefully we have quantum hardware ready in Busan City by 2026. And for education point of view, we hope to keep training more than 200 students per year after 4 years from now. And if we have 10 10 more members by the end of 2026, then we will find ourselves as successful as of 2026. And the most contents information that I mentioned in this session will be presented in our website, which is kqchub.com. And please take a look around the webpage and hope you enjoy and find it useful. That's all. Thank you. And please keep eye on us or our future quantum journey. Thank you.
Thank you for your informative presentation, Dr. Kim. As Dr. Kim said, if KQC collaborate closely with partners to achieve our goals, quantum technology are expected to be commercialized in Korea sooner than people would expect. Now, we are going to hear from domestic quantum experts. We will start with Dr. Daniel Kyung-Dok Pa, who is a professor of applied statistics at Yonsei University. He will give a presentation with the title, Quantum Machine Learning, Opportunities and Challenges. Please welcome Professor Pa.
Hi, everyone. Thank you very much for a very kind invitation. It's my great pleasure to be here. And I would like to thank everyone at KQC for having me for this wonderful event. I'm not sure what happened to my slide. The title is not showing up, but supposed to be quantum machine learning, opportunities and challenges. So I wanted to give a little bit of perspective on this quantum machine learning, and also at the same time, I'd like to give a little bit of taste on what my group does in Yonsei University. Okay, and again, so I'm from Yonsei University. I'm in the Department of Applied Statistics and Statistics and Data Science. And sorry that I have written my name in Korean, but I'm Kyung-Dok. Okay, let me see. All right, so I see that some things are broken, but I hope it doesn't cause any much problem. So I basically copied and pasted my research group webpage. So we are QDNA, and it has nothing to do with biology. It's quantum data science and AI. And we have 6 students and 2 researchers, so our group is growing, and I'm really happy for that. I'm really thankful for that. Just to quickly tell you what we do. So as our the name for our research group indicates, we try to harness quantum information theory to solve various challenges in data science and AI. And we also we are hoping to develop some industrial applications of quantum computing in the near future. And also there is a very important topic about how we deal with noise and imperfections in quantum computing. And we try to develop statistical and machine learning methods that fight noise and imperfections in quantum information processing tasks. And if you're interested, you could also visit our website. All right. So where does quantum machine learning started from? I see that the slide is a bit broken. I don't know why, but okay. Anyway, so this paper, well, this paper came out in 2009. Of course, the people talked about quantum machine learning even before that, but this is a paper that really brought a lot of excitement to the community. And if you look at this paper, what this paper says is that it says that if we use quantum computer, we can solve these linear systems of equations exponentially faster than with classical computer. In other words, we can do matrix inversion exponentially faster on a quantum computer than on a classical computer. And this brought a lot of excitement to quantum algorithm and also like machine learning community, because matrix inversion, it's something that happens, that appears quite a lot in data analysis in general. Like for example, like when we consider very basic like data analysis technique like linear regression, we have to do a matrix inversion on like a large covariance matrix. So this is quite common thing to do in data analysis. And this tells us that we can solve this basic subroutine on a quantum computer a lot better than on a classical computer. And after this paper came out, many people they went on and they used this technique as a subroutine to use for machine learning. But then that's all great, but in fact, this matrix inversion algorithm, which we also call HHL algorithm, named after the authors of the paper, is actually a lot. It's slightly more difficult than implementing the Shor's algorithm for factoring. Okay. In other words, this is, even though this is a great algorithm, we have no idea when we'll have a quantum computer that will allow us to implement such an algorithm. Okay. So again, like Shor's algorithm will be easier to implement on a quantum computer than this matrix inversion algorithm. So this is like a long-term perspective. Then we now need to consider then if we cannot use this wonderful algorithm for quantum machine learning in the near future, then what can we do in the near term? Well, people have worked quite hard on this topic, and there are a number of candidates. Okay, so in the near term, for near-term quantum machine learning, so I'm just going to list out a couple of topics. Like there's a kernel method. There's also like variational, in other words, trainable quantum circuits. There's like non-adiabatic quantum annealing, and usually people don't bring this up. They don't mention this. They just say quantum annealing. But it's very important to note that we're not doing adiabatic quantum computing. So it's a non-adiabatic quantum annealing. And they're also like quantum-inspired classical algorithms. And this is quite interesting because these algorithms, they are, like as the name indicates, these algorithms are inspired by like quantum mechanical principles, but we don't necessarily require quantum hardware. Okay, so we design algorithms based on quantum mechanics, but we run them on a classical hardware. And they could still be beneficial if our goal is not so much about reducing the runtime, but we care more about accuracies. Okay, and I also wanted to quickly mention that in conventional quantum algorithms analysis, usually like all of these like computational complexity analyses are done in the language of like big O notation, like it's done in the asymptotic limit. But in practice, the constant factor hidden in this asymptotic analysis is also very important. So in the near future, in the near term, for the near term quantum machine learning, we also need to consider, okay, maybe the quantum computer does not guarantee exponential speed up, or maybe even polynomial speed up, but maybe there is a constant factor improvement which we care about. All right, so from now on, so there are basically these 4 categories under near-term quantum machine learning, but I'm going to focus on these variational quantum circuits, okay? All right, okay, this is really broken badly. Okay, but let me try to, okay, so it was a really bad idea to use equations for this talk. But basic idea of these variational quantum circuits is to train a quantum circuit. First, parameterize quantum circuit, and then train such a quantum circuit to solve optimization problem. And then because like optimization appears in so many applications such as machine learning, chemistry, like finance, in so many domains, if we can somehow utilize this idea, then we can find many applications of quantum computing. But the key idea is let's say we want to solve some optimization problem. First of all, we need to define a loss function. And here, loss function is defined as some sort of quantity that we measure from a quantum circuit. So on the very left-hand side, I drew some abstract quantum circuit. And after we perform some measurement, because the probabilistic nature of quantum computing, we measure some expectation value. And that expectation value could be used to construct a loss function. And because quantum circuit is we design quantum circuit in a way that it's hard to simulate classically. We can say that such a loss function that we construct out of quantum circuit will be very hard to compute classically. Okay, so that's all great, but now we need to, once we define the loss function, we need some algorithmic means to reduce it, right? We need a way to kind of find the minimizer of such a loss function. And we know that the gradient-based optimization is quite useful for that. In other words, we want to be able to compute the gradient of such loss function with respect to the set of parameters. The good news is, so basically what this broken equation tells us is that in fact we can compute the gradient of the loss function with respect to the set of parameters using a quantum computer itself. Okay, so that's a really important point. So we can not only compute the loss function using a quantum computer, but we can also compute the gradient of the loss function using a quantum computer. Okay. In other words, we basically, we can from end to end, we can perform gradient-based optimization using a quantum computer. And this is really great news, because then we can just rely on a quantum computer for running over this optimization process, which could potentially be applied to many applications. Okay, but then, okay, so this is good. Analytical gradient can be calculated. Actually, we need a two quantum circuit measurements. Okay, that's great. But in this quantum-based optimization or quantum algorithms, what's known as expressibility is very important. This is a very complicated concept, but in short, basically we want to design our circuit and we want to parameterize our unitary gate so that with using the set of parameters, we want to be able to generate as many quantum states as possible. So we want to cover as much space on the Hilbert space as possible. So expressibility is quite important in this context. But it is theoretically shown. In fact, it is theoretically shown by those people who first suggested this variation of quantum circuit. They showed that there is this problem of what's called the barren plateau. This means that if we want to really go for expressibility, then this gradient quantity that we compute is computed out of expectation value, meaning that we have to repeat the same circuit over and over many times to compute the expectation value. But what this says is that if we want to go for expressibility, then such expectation value will vanish to zero exponentially with respect to the number of qubits. Okay? So this is very similar, even though at the fundamental level this is slightly different, but we could compare this to the vanishing gradient effect when we train deep learning. So this was a bad news, right? Because we can compute the gradient using a quantum circuit, but the gradient will become exponentially small with respect to the number of qubits, meaning that the number of repetitions that we need to perform in order to estimate the expectation value will grow exponentially with the number of qubits. Okay? So, perhaps we might have to sacrifice a little bit of expressibility, which is very similar to putting a prior distribution to our problem, and that could vaguely correspond to designing these variational quantum circuits with some specific structures to kind of give up on expressibility to avoid barren plateau effect. So once this barren plateau effect was suggested in 2019, ever since that, basically, most of the quantum machine learning research based on variational quantum circuit is about how we avoid barren plateau effect while maintaining the quantum advantage. It was found that barren plateau effect could be avoided by using such structure. So I'm not going to go into all the details about this structure, but the basic idea is that we start from some number of qubits, And then, so these blue and red areas, so blue rectangle and red circle, those are the gates that we parameterize with the model parameter. But basic idea is that we start from some number of qubits, here for example 8 qubits, and progressively we throw away like half the qubits. Okay, so we progressively reduce the number of qubits all the way down to 1. But once we perform measurement on the very last qubit, we either obtain 0 or 1. So perhaps we can use that for doing a binary classification. Okay, and such a structure is very interesting. First of all, as I said, there's no barren plateau effect if we exploit such a structure. And what's also interesting is that the number of model parameters that we need to optimize scales logarithmic to the number of input qubits. And usually the number of qubits we need to use for encoding classical information is also logarithmic to the number of features that we have in the classical data. So when we look at the number of model parameters to the number of features that we have in the classical data, it's like a double logarithmic smaller number of parameters that we have to optimize. So it's like extremely compact model for machine learning. And this has like a shallow depth, and we train gates, and this only requires 1 qubit measurement. So we thought this is an excellent fit for near-term noisy intermediate scale quantum computing. So we did some benchmarking on this quantum circuit. We used, so this was just a classical simulation of the quantum algorithm. We used 8 input qubits to train the circuit to do binary classification on MNIST data. Like we were hoping that a quantum circuit will distinguish 0 and 1, and also the quantum circuit could distinguish shorts and pants. So we tried these 2 different binary classification tasks. And the results were very promising, even though this is only like a numerical simulation. We saw a very good performance on a quantum computer. So for example, when we look at the MNIST data classification, we have all these bar graphs from 1 to 10. These are like 10 different ways to parameterize the quantum circuit. So we tried a variety of sets of models, and what the number that you see on a bracket, like ranging from 12 to 51, they are the number of model parameters that we had to use to train those quantum circuits. So the number of parameters, again, they're only from 12 to 51. And despite having such a small number of free parameters, the classification test accuracies were very high. Like they are at least like 98%. However, if we compare that to like classical, like state-of-the-art CNN, of course that's not as good as the state-of-the-art classical CNN. But we have to keep in mind that classical CNN typically uses like hundreds of thousands of free parameters, up to even like millions of free parameters. So we thought maybe it's not a fair comparison to compare our like compact model to more complex CNN model. So we downgraded the classical CNN model so that the number of model parameters are comparable to the range of 12 to 51. So for example, we designed the classical CNN with 44 parameters. And this really, like, when we look at it from classical machine learning perspective, this doesn't really make sense. But just for the fair comparison, we downgraded classical CNN. And what was interesting to see is that when we downgrade classical CNN to have just a small number of parameters, the performance was actually lower than what we could achieve on a quantum computer with similar, with basically the same training condition. Okay, and we have observed something very similar for this fashion MNIST data as well. So this was very encouraging and promising result. So basically, if I just summarize this result in like one sentence, we observed higher accuracy on a quantum computer in the few parameter regime. So this happened only in this regime. And of course, it will be interesting to scale it up, but for now, we only observed such an advantage in the few parameter region. Okay, and then like before waiting for we have a quantum hardware with which we can really scale up this quantum circuit, we thought about how to like fully utilize such nice feature of this quantum CNN. And we thought maybe transfer learning would be a very natural place where we could apply this idea. So we tried classical to quantum transfer learning. So we pre-train a CNN. So this is classical CNN using like specific set of data. And then once we have this, then now this will serve as a base. And then now we train a quantum convolutional neural network for completely different task. So here, the classical CNN is trained to discriminate like this fashion and NIST image data set. And now we use that reference, and we basically truncate some of the layers at the end, and then we basically attach quantum CNN to this classical CNN as as to fine-tune the model specific to the new data set. Okay, this is a very common idea that people often do in classical machine learning. And so we by simulation, we also compared classical to classical transfer learning and classical to quantum transfer learning. And we have tested this for doing a classification between 0 and 1, 2 and 3, and 8 and 9. And in all cases, basically, there are lots of bar graphs, but basically all these like bar graphs, they are obtained from this classical to quantum transfer learning, whereas the solid lines are obtained from classical to classical transfer learning. And these results were quite promising because they all support that it will be more beneficial to do classical to quantum transfer learning rather than purely classical transfer learning. All right, so these are all empirical studies, and we wanted to understand this from more foundational, like fundamental perspective. So we were asking this question: so what does a variational quantum classifier really do? And in the end, it's just doing what's known as quantum state discrimination. And maybe this terminology is not very familiar to many of you, but this is an idea that came out even before the birth of quantum computing. So people in like 1960s, 70s, and thought about how to design such a measurement that discriminates two different quantum states. And sorry about the broken equation, but basically this quantum state discrimination problem can be framed as some optimization problem. And in I think it was like 60s, Carl Hellstrom actually solved this optimization problem for the binary case. So in the binary case, we can write down the optimal solution analytically, and it's known as Hellstrom measurement. So in the binary case, we know the bound. We know how good we can do. It's known as Hellstrom bound. And what's interesting about this Hellstrom bound is that, in fact, given these two quantum states, rho 0 and rho 1, so these are the quantum states that encode two sets of classical data. One belongs to class 0, and second, the set of data that belongs to class 1. Okay, so rho 0 and rho 1, they represent like quantum encoding of the given classical training data set. And basically, what the theory that we can see from this quantum information theory is that once the state encoding is given, then whatever we do on it, on a quantum circuit with a quantum computer, we can never increase this bound. This bound only decreases. Okay? And this is very important to understand from fundamental point of view. And so basically, variational quantum circuits that, whatever people say about it, it's all about the training accuracy is completely determined by classical to quantum encoding method. And once that's given, variational quantum circuit simply tries to reach this bound. It tries to find the optimal set of measurement to reach that bound. That's it. So of course, from fundamental perspective, it's very important to think about how we go beyond this limit, and this only tells us about training errors. So what about the test errors? So there are many interesting questions that spring from this theoretical analysis. So we thought, okay, so one way to go beyond this limit is to train the map that's specific to the data set, because here are all the variational quantum circuits that they train the same map for all the data sets. So we thought maybe we can think about training a map that's specific to training data set. Then perhaps we can avoid this bound, and that actually corresponds to a one-class classification. Okay. So in one-class classification, this is slightly different compared to binary classification. It's slightly more difficult than binary classification because the data set that we have for one-class classification, which aims to train the map that's specific to the data set, that does not have the label information. So this is a little bit more difficult problem than binary classification. And just to make this story short, the final story is that the quantum model uses, again, an exponentially smaller number of parameters compared to the usual classical models. Nevertheless, the quantum one-class classification performs comparably well to the well-known methods like kernel PCA, one-class SVM, and also deep convolutional autoencoder. Okay. So maybe I'm not sure if I'm running a little bit out of time, but finally, I wanted to say that, well, basically this everything that I talked about, this Hellstrom bound and so on, the theory of quantum state discrimination basically tells us that the general measurement in quantum mechanics, which is called positive operator valued measurement, POVM, can actually distinguish non-orthogonal states, okay? And this is indeed the foundational difference between quantum and classical when we do classification, okay? So we thought about designing a quantum circuit that directly implements an arbitrary POVM, and we try to parameterize a quantum circuit that directly implements POVM, and we try to train that circuit to perform like multi-class classification that distinguishes non-orthogonal states. And maybe on the right-hand side is the main result. So we tried that on very simple iris data set to do like a 3-class classification. And the end of story is that the quantum multi-class classifier based on this POVM performed very well. All right, so I have listed a couple of open problems for near-term quantum machine learning. As I've already said before, variational quantum circuits or variational quantum algorithms, and also like non-adiabatic quantum annealing, they are very popular approaches for near-term quantum machine learning. But we need to be careful because we need more theory needed to make like strong claims about quantum advantage, and also we need to be able to avoid barren plateaus effect while retaining the quantum advantage. And also a lot of results are given under like empirical studies. So it's important to understand how quantum machine learning methods scale to large problem sizes. And as I've already indicated through this analysis with Hellstrom bound, quantum data preparation is a very important topic. For example, how to encode classical data efficiently as a quantum state. So this is really, really important topic. Okay, and I've mentioned something about improving the binary classification beyond the Hellstrom measurement. And finally, as all of you know very well, that we need to take care of shot noise and hardware noise. Okay, and that's it for my talk. And thank you very much.
Thank you for your wonderful presentation, despite of the incomplete material status. It was very helpful to understand how we should approach quantum machine learning. Our next speaker is Dr. Byung-doo Oh, who is a CTO in charge of developing quantum algorithm in Baobab A Bio. Baobab A Bio is the quantum mechanics-based synthetic and protein drug design technology company, and recently joined the IBM Quantum Network through KQC Hub Busan. He will present a topic on quantum computing for new drug design. Please welcome Dr. Oh.
Thank you for inviting me for this nice event, and I really congratulate to KQC Hub Open House. My name is Byung-do Oh, and from Baobab A Bio and Seonggyun University. The title of my talk is Quantum Computing for New Drug Discovery, and many parts of my presentation biographs were prepared by Professor Kyung-tae No, who is the CEO of Baobab AI Bio. This shows a workflow of drug discovery, and at first we need to obtain target protein. So we need to do target protein structure analysis, and then find binding pocket analysis to find binding place to our target. So this is like generating molecule, protein binding site, and drug fragments. This structure analysis is very important. And then we make a lot of customized potential drug candidates and make a library. And then from that library, we virtual screening by using computer, and typically ligand-based screening and structure-based screening. We get hit compounds. Hit means exhibits significant medicinal activity against the disease. And then do another kind of screening with in silico toxicity and pharmacokinetics and other physical properties. We get lead. Lead is a smaller set of better candidates. So before clinical studies, we need to do many steps to do drug discovery. So every step, the quantum computer can be used. And also a cryo-EM, which is a Baobab's very recent new machine, can do a protein structure analysis very well. So our drug discovery strategy is to dramatically reduce the time and cost of small molecular and protein drug development by introducing cutting-edge innovative technologies such as quantum computing and cryo-EM. And through those technologies, we would like to do drug discovery with our own pipeline, as well as in collaboration with other companies or institutions, and would like to platform provide service. And these are the list of cutting-edge technologies, which are mechanics-based drug design tools, so quantum mechanics-based, and AI-based drug design tools, specifically generative models and deep learning, and structural determination of protein and protein drug complex using cryo-electron microscope, and QC algorithms for quantum computing to in silico drug design. And Baobab A Bio and Bioinformatics and Molecular Design Research Center, which is in Yonsei University, are working very closely and has capability CADD platforms. CADD means computer-aided drug design, and QC CADD application and AI platforms and many drug design experts. This is a roadmap of quantum computing application for cryo-EM analysis. At first, we need to get target protein with sequence information and generate 2D electron scattering image with cryo-EM single particle analysis. And by using this cryo-EM machine, we get thousands of 2D scattering data. With these scattering data, we can make 3D electron density And from 3D electron density, we can reconstruct 3D protein structures. And then by docking simulation with QM, we can determine ligand protein complex structure. So as you can see, there are three pictures, same pictures of quantum computer in three different places. The quantum computer can be used for each different process steps. So quantum computer can reduce the data processing time of cryo-EM significantly. So this is very important for us. And then quantum machine learning, you have already get a very good introduction from previous speaker, Professor Park. And the quantum machine learning are explored in all development stages of molecular design with desired properties. And quantum generative models are used for learning latent representations of molecules and generating large amount of drug candidates. I will explain in a little more details about this. And quantum generative models have the relative advantage to cover the entire distribution because of the intrinsically probabilistic nature. And among quantum generative models, we are especially interested in quantum generative adversarial networks. And deep generative models are used for various representation types of molecules, such as string-based, graph-based, and shape structure-based. So quantum computing can offer a unique advantage over classical computing for drug discovery by using quantum chemistry simulation as well as quantum machine learning. And also, the quantum hardware is getting improved. It is improving every day, like IBM is improving every day. So we can use, if we utilize a quantum computer, we can do our drug discovery more efficiently. And quantum GAN, which you have already heard from, again, Professor Park, it has a very strong expressive power in learning data distributions with much less parameters. So it can speed up learning and training, and it has the ability to search exponentially growing chemical space with increasing qubit count. And near-term quantum computers, which is still error-prone, like IBM quantum computers, are very useful for quantum GAN. And hybrid GAN model is used. As already seen previous talk, the quantum computer and classical computer we can use together in hybrid fashion. Then the quantum GAN mechanism with a hybrid generator and classical discriminator can be done. And also, by using classical computer together, it requires fewer qubits, but still exploits the benefits of quantum computing. This shows schematic diagrams of two quantum computing paradigms. The first one is just using quantum computer, quantum circuit in its input state and quantum circuit, and at the end it has a measurement readout. This is a standard gate model quantum computing. But nowadays in near term, which has errors, as you have already seen this variation of quantum computing with the quantum part and classical computer together. So in quantum part, in this quantum circuit, there's a gate with parameters, and after the operation, gate operation and measurement, if it input to classical computer, then a classical computer does optimization and propose better parameter to quantum circuit, and it goes on. So until they have, for example, ground state energy of some molecular structure. So this variation of quantum computing is very important for near-term quantum computer. I will show one example how quantum computer is being used for drug discovery. This is a QGAN, as I mentioned, which shows a generator part and discriminator part. This is a generator try to make many synthetic molecules, and discriminator discriminate from real molecule distributions if it's the input molecule is real or fake. So it discriminates between these two, and generator would like to cheat so that it make this molecule as close as this real molecule, so discriminator cannot discern which one is real and which one is fake. So by training, at first train the generator make many molecules, and then discriminator trained for a while, and then generator train again and go back and forth until it make a very similar molecules. So this kind of things can be done in classical computer, but with quantum computer, it's this latent space. This is use some random noise, which is more efficient in quantum computer. So in this case, string-based, this one is a string, indicates some molecular strings, but sometimes use the graph-based, which is like example here. The node is atom, and this H is bond. So atom vector and bond matrix, we can use those and make this graph. As I mentioned, this generator is hybrid. So quantum part and classical part here, and discriminator in this case is used for as classical computer is used. So this shows a more detailed schematic of drug discovery process using quantum GAN with hybrid generator. Here, hybrid means, as I mentioned, this is a quantum part. This is a classical stage neural network. And then at the end of this circuit, it can generate atom vectors and bond matrices. And then from that information, we can reconstruct synthetic molecular graphs. And if it's, we can make as many as fake molecules. And real and fake is a discriminator. And we use, they use a metric of a Frechet distance, which is similarity between two distributions, and also drug properties, so that they can make many drug-like synthetic molecules. If we look at hybrid generator a little more detail, then as I mentioned, this is a quantum part, this is a classical part, and initialize at first all 0, and Ry and Rg rotation with G1 and G2 angle. And then this is entanglement part with Ry rotation, and this one shows control rotation Z in 2-qubit gates. So we can repeat this part L times, and this theta 1, theta 2, up to theta 2n minus 1 are parameters we need to optimize. And after the measurement, this is a vector. This feature vector is an input for classical stage, and then after the neural network, then we can find, we can generate new synthetic molecules. Okay. So, in summary, I have shown one example of how drug discovery can be done by using quantum computer. And so this left side part is a de novo digital drug design platform. We hope to generate billions of molecules within 2 weeks, and screening about 1,000 hit molecules, and then about 10 molecule lead, and then experimental result and find the candidate. And this kind of process is being done now by using classical computer machine learning. But we hope with quantum computer we can accelerate this process. And Baobab has this kind of capability, and KQC will have a very advanced quantum computer like 433 qubit IBM quantum computers. So we really hope can work together and produce very nice results. And business types, as I mentioned, we can do customized service according to customers' request, and joint research for purpose of IP share, and hit lead candidate development of our in-house pipeline. And thank you very much, and congratulations again.
Thank you for your presentation, Dr. Oh. Drug design is one of the key sectors where quantum computing can make a big difference in the future. KQC will keep collaboration on the research with Baobab to have a positive impact on their efficiency and productivity using quantum computing. KQC is a research-based company. As it is supposed to be, KQC runs multiple internal research projects on quantum computing. The last session is from Mr. Hyung-Kyu Min, a researcher at KQC. Today, his topic is variable selection via QAOA. Please welcome Mr. Min.
Thank you. Sorry, I'm a little bit nervous. This is our last session. Let's start. Hello, my name is Hyung-Kyu Min, and I'm a researcher of the Korea Quantum Computing. Today, as a researcher of the KQC, I'm going to introduce our research project. Most of our research team members are majoring in the data science and statistics. Therefore, the KQC research team have focused on applying the quantum algorithm into data science problems. One of our main problems is variable selection. Today, we're going to see our research project about quantum variable selection. First of all, we're going to see our target problems. Our target problem is variable selection, especially of the linear models. The linear model is rhetoric model analyzing the linear relation between input and output. For instance, we can analyze the reaction between weight and height using the linear model. The term linear can be understood as linear combination of the linear algebra. The linear model builds the model using linear combination of design matrix like y equals beta 0 plus x1 beta 1 plus x2 beta 2. It is safe to say that the linear model is most important model in the data science. First of all, the linear model is important because almost every statistical analysis and data science models are based on the linear model. Therefore, by studying the properties of the linear model, we can develop the result into other models. Secondly, the linear model is a parametric model that can give us a powerful statistical inferences. For instance, it can give statistical test about significance of height on the weight. A lot of fields such as biology, commerce, and social science use the linear model as a framework of statistical inference. For this importance, we choose the linear model as our target problem. However, there is a big obstacle in building linear model. If the number of features is too many, it will increase the standard error of the estimator of the relation. If it is, the model's statistical inference and predictive power are really hampered. So we have to shrink the number of features by selecting them. The variable selection is literally the problem of selecting the variable used at the model. The variables can be seen as pictures, factors, or prior information to predict some target variables. For instance, let us assume there is a data about patients of internal medicine. We have information about patients' height, diet, age, and etc. If we want to figure out what and how some factors affect on the lung cancer, we can use the information to see. However, if you use too many numbers of the factor, the model cannot capture the exact reality. For instance, because the region and nationality are similar with each other, they might be insignificant in the model when using both of them, although they are significant when using only one of them. Therefore, we have to select the factors to see exact effects. The problem is, it is hard to find the optimal combination of the factors because the information of each variable is correlated with each other. Therefore, to see the best combination of the features, we have to explore every combination of the features. If you have p numbers of the features, the number of the combination becomes p to the power of 2. For instance, if you have 10 number of the features, then the number of the all cases becomes 124. If you have 100 of features, it's almost 30 to the power of 10. To have the understanding, the total number of bacterial cells on Earth is estimated as 5 times 30 to the power of 10. Now, let's see how can we solve the problem. The conventional statistical approach is Russell regression. The Russell regression using L1 penalty to find the coefficients. By restricting the data, the algorithm tends to set the coefficients of uninformative feature as 0. Therefore, the uninformative features are naturally eliminated. The Russell is really powerful and fast, but its estimator is biased. Therefore, to use the Russell coefficient, there need additional statistical inferences. Compared to A, the genetic algorithm is approached based on the optimization theory. It is used at the optimization problem with a lot of local minima and intractable structure. The genetic algorithm is an algorithm imitating the evolution process in nature. It finds best solution by evolving generation of candidates through selection, reproduction, and mutation. It is powerful and flexible algorithm, but it is super heuristic algorithm, which have too many parameters to handle. The simulated annealing is also an approach based on the optimization theory. The simulated annealing is algorithm imitating the annealing process. By repeatedly going up and going down the hill, it can avoid local minima and find global minima. It is also efficient and powerful algorithm. However, the solution of it is inconsistent, and like genetic algorithm, there are too many hyperparameters to handle. On the other hand, there is a quantum approach to solve the combinatorial algorithm. Based on the theoretical and experimental study, the quantum approach is expected to show better performance at the combinatorial problem than classical algorithms. It shows relatively good performance even when the scale of the problem becomes bigger. The base work of our project is quantum feature selection, published at the 2022. The paper suggests algorithm aiming to optimize the following objective function. The objective function contains 3 components. The first one is redundancy term, which is embedded as Q. The redundancy could be understood as degree of information overlap. The algorithm eliminates the redundancy among the features. It can be understood through max-cut problem, which is explained at next page. The second criterion is importance, which is embedded as beta. It is the amount of information that each variable contains. If the importance of some variable is large, it is likely to be selected. In the base work, both of them are measured by mutual information criterion. The final term is hyperparameter calibrating the weights between the redundancy and importance. Now, let's see the max-cut problem to see the details of eliminating the redundancy. The max-cut problem is graph problem to assign level on the nodes by penalizing or rewarding the coexistence on the same levels. Let's see the following graph. As you can see, we can assign 1 or 0 levels on each node and make some clusters. By assigning them, we can see that there is a connecting line between two clusters. The mask problem is a problem about maximizing the sum of the weights of the connecting lines. For instance, the values of case 1 is 1.7. The values of another case are 2.6. Therefore, the below combination is more appropriate solution than the above one. The original mask problem binds nodes with small weights against those with large weights. Similarly, the quantum feature selection binds features with small similarity against those with large similarity. As a result, it can eliminate the redundancy. The base work used the criterion of redundancy and importance as mutual information criterion. However, the mutual information criterion is inconsistent along hyperparameter and too general measure for the linear models. Therefore, we suggest Pearson correlation coefficient to capture the only linear relation among the features and targets. Let's see the detail. Let's see the result of experiments using our approaches. To see the performances of our suggestion, we executed 3 experiments. The first one is compare between previous works and ours. That is, we compare the correlation and mutual information criteria. The second one is compare among conventional algorithm and quantum algorithms. For the first and second experiments, we generate data following multivariate normal distribution and use first 4 variables as true influential variables on Y. Lastly, we also did experiments over a real data set whose number of features are 9 to 30. We used performance metric for prediction as mean squared error, AIC, and R squared, and metric for multicollinearity as conditional numbers. All of them are broadly used metric at evaluating the linear models. The first experiment is compare between correlation and mutual information criterion, aka MI. The blue line depicts the cost of all possible cases. We visualize the 10th power of 2 numbers of cases into decimal number. That is, binary numbers into decimal numbers. Because we use first 4 as true parameters, the combination of 1, 1, 1, 1, 0, 0, 0, 0, 0 becomes the optimal sort combination. The decimal number of 1, 1, 1, 1, 0, 0, 0, 0, 0 is around 1,000. So we can see that the score is best when it reaches at 1,000. The crimson line and green horizontal line depict the score of solution of each algorithm. For instance, the combination of MI got 3,000 at AIC score, and combination of correlation got almost 0 at AIC score. All of the 3 criterions are better when they are lower. The correlation measures always got better score on all of the 3 metrics than mutual information criterion. Therefore, we can say that we found better method for the linear models. Next, we performed Russell genetic algorithm, aka GA, and simulated annealing, aka SA, and quantum annealing, aka QA. As we can see, even though all of the 4 algorithms are succeeded to find combination with good R-squared, the conditional numbers of Russell, GA, and SA are not that good. Therefore, we can say that the solution of quantum annealing is good at both of the predictive power and analytic power of the models. Finally, we did the experiments over 5 different real data sets. It is better to be high for the coefficient of determination and better to be low for the conditional number. As we can see, the quantum annealers are not that good at prediction, but good at conditional numbers. Because 2 criteria or in some kind of trade-off relation, we can regard that the quantum algorithm can find a combination good for explainability by sacrificing the performances. Anyway, the results show that the quantum approaches can be used at the real data too and have some advantages. As a conclusion, we can summarize our works as finding more appropriate measures for the linear model and show the quantum variable selection can be used at the real data application. So this is the end of our research on the quantum variable selection. Based on the researching experience, we are planning to study applying the quantum algorithm into other problems. To efficiently organize the research direction, we are considering 3 steps: applications, data, and methods. The applications fields are front field where the most of the users are interested in. The biology, finance, and logistics are fields that where the problems are made. However, most of the application fields have data problem, which means that the structure of data is too complicated that they have to be handled by professionalists of the data. Because of the KQC has many experts on statistics and data science, we're expecting that we can show our strengths about it. To solve the problem, we will keep research the quantum approaches in the conventional methods such as dimensional reduction, Bayesian statistics, and machine learning. Through the framework, we'll keep figuring out the potentials of the quantum computers as a pioneer of the quantum computing in Korea. Thank you for listening our presentation.
Thank you for presenting an excellent review of the research, Mr. Min. Today is just the beginning of internal research sharing. We will create opportunities to share KQC's research and project more often in the future. Now there will be a closing remark from Dr. Junyoung Kim, CEO of KQC. Please welcome Dr. Kim.
Well, good afternoon. Thank you so very much for coming here today. And I would like to thank all the distinguished guest speakers and keynote speakers from all over the world, basically. And the also distinguished audience, online and offline. And well, perhaps quantum computing to many people, not the people in this room, is still a very foreign concept. I hope today's discussion and presentations may give you some takeaways and insights about quantum computing. And well, some may say it will take more than a decade for quantum computing to can do something actually useful and viable in commercially viable way. But I dare to say I beg to differ. It's very near to us. It's now distant future. It is just around the corner. Well, even some scientists don't understand exactly why matter behaves as it does at the quantum level, and yet they are getting better at exploiting its peculiar dynamics in ways that may soon overturn the technology businesses, as we know. And it's not, maybe it's not a coincidence that Nobel Prize winner this year in physics was awarded to the 3 scientists who conducted groundbreaking experiments using entangled quantum states, where 2 particles behave like a single unit even when they are separated. So you, I mean, this actually can tell you a lot that quantum computing is being researched and being invested a lot in business world as well. that actually can show as the actually Nobel Prize winner in physics relate to the quantum computing. And you have learned today that there are some significant researches and developments are being done in quantum computing space. And many resources and brain power are being invested in quantum computing to make a positive contribution to the mankind. And well, I mean, let's be honest, but 20 years ago, if you remember Netflix service, nobody fathomed that you can watch the favorite movie on your cell phone 20 years ago. And back then, Netflix was sending your list of DVD in regular mail with return postage. I know that because I used that service 20 years ago. And 10 years ago from today, nobody spoke out loud about quantum computer. But here we are. Quantum computer is just with us. And today, we have 100 plus qubits quantum computer today and maybe over 1,000 qubits from next year. What we may think impossible now may well be our reality in 3 or 5 years' time. And we may take it for granted in that when that time comes. So KQC is actually very proud to be the part of the global quantum computing society, and also feel a grave sense of responsibility at the same time. And we will make the very best efforts to make our imaginations into reality and help building quantum ecosystem. And each and every one of you is a part of our ecosystem, and you have to be the quantum computing evangelist from today. And thank you so very much again, and we'll see you soon in our next quantum computing seminar events. Thank you very much.
Congratulations. Thank you, Mr. Gi. Now we have reached the end of IBM Quantum KQC Hub Busan Open House. Wrapping up our open house, I would like to thank you for joining our event out of your busy schedule. Also, special thanks to our presenters who made an excellent presentation despite of some of the technical problems. We will prepare much better than today. Please stay tuned for our latest updates, and we hope to see all of you again at our next event. Thank you.